Uh, okay, in today's video, I want to talk about cardinal arithmetic and a little bit about ordinal arithmetic too at the start. So, when we have cardinals, we can add them and we can multiply them, and we can also do exponents with them, which I'll talk about perhaps later on in the video. And with ordinals, we can do the same thing. There are lots of standard properties that arithmetic have, which lets us do lots of algebra, and we need to establish that these properties actually hold. A lot of these properties have standard names, such as being associative, which says you can basically bracket things how you want, and being commutative, which says you can order things how you want. And these are the list of properties which I think are the most important to deal with today. So before we tell you about these properties, I have to define the symbols I'm using. I haven't told you what addition is. I have not told you what multiplication is. And I don't remember I even told you what 1 is. I told you what 0 is, certainly. It's the smallest ordinal or cardinal. But we need to define a bunch of stuff first. And I'll also do this a bit for ordinals. I think it makes sense to do ordinals before cardinals because they're sort of more fundamental. Okay, so definitions. So if alpha and beta are ordinals, then I define what it means to add and multiply them. Note that cardinals are ordinals, and the definition of cardinal operations is not the same as the definition of ordinal operations. So you have to infer from context whether it means to use the ordinal operation or the cardinal operation. It will usually be obvious, and I'll explain to you in the cases that it's not which one I mean. So first, the ordinals, I'm doing ordinal operations first. Then we define alpha plus beta to be the ordinal, which is order isomorphic to the disjoint union of alpha and beta. And I have to tell you what the order is. Before I do that, I haven't told you what disjoint union is. At least I don't think I have. So the disjoint union is like basically you take the union, you take the things which contain both sets, but we want to pretend that the sets are not have no things in common, even if they do. So uh, sub definition, which will be useful in general. If A and B are sets, then the disjoint union of A and B is defined to be equal to the union of the stuff in A with a 0 tagged on it. So A times the set containing 0 union B times the set containing 0 plus, which we'll see later is the number 1. Okay, so here we've got this new set. It has a copy of A in it, where each thing is tagged with a 0, and it has a copy of B in it, where everything is tagged with a 1, and that's all the elements. And these two things have nothing in common because the tags are different. If you're in the first chunk, then you're a tuple with the second, or you're a pair with the second entry being a 0. And if you're in the second one, you're a pair with the second entry not being a 0. So these are not the same. So you take, so back to the ordinal, we take the disjoint union of alpha and beta with the order uh, A is less than or equal to B if either A belongs to alpha, so A is equal to A prime 0 for some A in alpha, uh, and B is in beta, B is equal to B prime 0, 1, so 0 plus for some B in beta. So either in different parts, and the the bigger one is in the right part, the part of beta, or they're in the same part and they're just bigger with the normal ordering, or a a is equal to A prime 0, B is equal to B prime 0, with B prime is greater than or equal to A prime, or finally they're both in the right part. A is equal to A prime 0, sorry, 0 plus, and B is equal to B prime 0 plus, with a prime less than or equal to b prime. And here they're ordered using the ordering of the ordinals as elements of beta. So there are three cases: either in the same part and they're compared the normal way, or they're in different parts and b in the second part, which is the more important part. Okay, this gives us a well-ordered set. So note that this is a well-ordering. If I have a non-empty subset, it either intersects the alpha part or it doesn't. If it does, then its smallest element will be in the alpha part, and it's the smallest element which it has in the alpha part, or it's all in the beta part, in which case it's the smallest thing in the beta part. So every non-empty subset has a smallest element. This is well ordered. And we've proved, at least implicitly in the previous videos, that every well-ordered set is order isomorphic to an ordinal, and in fact a unique ordinal. So this gives us a well-defined notion. So if I have two ordinals, I just take this construction end of it. This is a well-ordered set, and I just find the unique ordinal, which is order isomorphic to it, and uh, that gives me our way of combining two ordinals. Okay, so example, which is an important example, is the +1 example. So I haven't told you what 1 is. I don't think so, but here's the definition. So we define 1 to be the successor of 0, as I hinted at several times in the previous discussion. So if alpha is an ordinal, then alpha +1 is the unique ordinal, which is order isomorphic to the disjoint union of alpha with 1. So this is the ordinal order isomorphic. So there's a bijection from alpha from this set to the ordinal, which preserves the order, to alpha disjoint union set containing 0, because that's what 1 is. Which you may notice is this one is order isomorphic to, this is an isomorphism type symbol, alpha union the set containing alpha. You just map 0 to alpha. And this is the definition of alpha plus. So alpha +1 is equal to alpha plus. And from now on, I'll probably just write alpha +1 instead of alpha plus, because it's sort of more reasonable looking notation. You have to keep track of pluses in the superscripts. So we can always just add a 1 to an ordinal to get the next ordinal, which makes sense. It's consistent with our notion of how addition should work. And this is another useful example. I'm going to go with another new definition. We define 2 to be the successor of 1. It's the number after 1. So in particular, 1 plus 1, the thing after 1, is 2. So we've now established that 1 plus 1 is 2. It took a lot of math, but you got there. Okay. So this is how addition works. And it's yes, more useful to use it when we have more examples of ordinals we care about. But all the finite numbers you usually care about are ordinals, at least like the whole ones, the whole positive ones. And you can define the other ones using those, but we'll do that in a later point. Okay, so this is addition of ordinals. And next I want to do multiplication of ordinals, and then I can move on to cardinals, which will follow a similar sort of pattern. So definition. This is multiplication of ordinals. Okay, so similarly, we're going to take two ordinals and we're going to define a new well-ordered set from them, and then we're going to define the product of the two ordinals to be the order type of that well-ordered set. So if alpha and beta are ordinals, then we define alpha beta to be the ordinal which is order isomorphic to this thing. So we take alpha Cartesian product beta. Remember, this is the set of all pairs A, B, where A is in alpha and B is in beta. And we order this by saying we care about the first coordinate more. So this is lexicographic ordering, ordered by A, B is less than or equal to C, D if and only if uh, A is less than or equal to C, or A equals C and B is less than or equal to D. So you might be tempted to say, well, just make it bigger if they're bigger in both coordinates. It turns out this doesn't give you a total ordering usually, so we can't do it like that. So what we do is we just say we care about the first coordinate more than any other coordinate. And then if they happen to be the same, we'll then look at the second coordinate. So now everything is comparable because everything has a comparable first coordinate. And if they're equal, they have a comparable second coordinate. And this is well ordered. If I take any subset of this Cartesian product, there is a smallest thing which occurs as a first coordinate, and among those things, there's a smallest thing which occurs as the second coordinate. So this is a well-ordered set. Okay, so this gives us a definition of ordinal multiplication. I don't plan to use this very much, but I thought it would be amiss to not bring it up. But I really want to focus on is cardinal arithmetic and establishing it has the properties we care about. So, cardinals, arithmetic, definitions. Okay, so you may guess how this works from the ordinal ones. It is basically the same idea. So if, let's say, I'll use alpha and beta again. We'll think of them as cardinals this time. If alpha and beta are cardinals, then we define alpha plus beta as a cardinal to be the cardinality of the disjoint union of alpha and beta. There's a unique cardinal in bijective correspondence with alpha disjoint union beta. And we define alpha times beta, which is alpha beta, to be the cardinality of the Cartesian product of alpha with beta. And in fact, let's go on to exponents as well, because I'll talk about those near the end of the video, and this is a convenient point to sneak them in. So we do alpha to the power of beta. This is the cardinality of the set of functions from beta to alpha. And in general, if you have a set to the power of another set, this means the set of functions from the top set to the bottom set. This is the cardinality of alpha to the beta, where this means the functions, so which is the cardinality of f from beta to alpha. And these have lots of nice properties, which we want to establish. Okay, so remarks. So with finite cardinals, this works the same as with ordinals, basically, because every finite ordinal is a cardinal. So if alpha is finite, then by the same comment as before, alpha plus 1 is equal to alpha plus. Yeah. And this agrees with the usual ordinal thing. And in addition, for the cardinality of the sum of two ordinals is the sum of the cardinalities, and this is also true with products. So these constructions agree with the ordinal constructions, at least in terms of cardinality. I didn't mention exponents for ordinals. It turns out for ordinal exponentiation, it actually doesn't agree with cardinal exponentiation, which is part of the reason I didn't bring it up, because it's sort of messy for our purposes, and I don't plan to use it. But this is a thing to keep in mind. When people talk about ordinal exponentiation, they typically don't do the same thing as cardinal. In fact, like it could be the case that you can have a set to the power of another set as an ordinal, and the cardinality of that set is smaller than the cardinal corresponding to the cardinal definition. Okay. So I want to establish that it has all the properties we talked about at the beginning of the video. So proof of properties Now we need to prove the properties. So proof of cardinal arithmetic properties. Okay, so I'm going to go through them all in order, and we can do some fun stuff with exponents at the end. So I first want to prove that plus is associative. So let alpha, beta, and gamma be cardinals. I want alpha plus beta plus gamma is equal to alpha plus beta plus gamma. So how do I show the two cardinals are equal? Well, I define a bijection between them, or equivalently a bijection between the sets which define them. So we need only find a bijection. We need a bijection phi from the things defining these. So this is alpha disjoint union beta disjoint union gamma to alpha disjoint union beta disjoint union gamma. And this does exactly what you think it does. So define phi. So it takes in a thing. So a thing which comes from the alpha copy looks like this. It's got an A and it's been tagged with a 0 and then tagged with another 0. I'm going to map it to the thing in the alpha copy on the right, which is just an A tagged with a 0. And then I do the similar thing for the other one. So B is tagged with a 1 and then a 0. And I phi, and I map this to B, and now it's tagged with a 0 and then a 1. Because it's in the right half of the right disjoint union within the left half of that right half. And then with C, C is tagged with a 1 only in the first part, and it's mapped to a thing which is tagged with a 1, and then that thing is tagged with a 1. And this is a bijection. It's routine to see that this is a bijection. So these two cardinals have the same size, and so they're the same cardinal. Okay, next I need to do the plus is commutative. So we want let alpha, beta be cardinals. We want alpha plus beta equals beta plus alpha. And again, we can define this, we can do this with a bijection. So define phi from alpha disjoint union beta to beta disjoint union alpha by phi of A0 is equal to A1, which maps it to the thing on the right, and phi of B1 is equal to B0. So basically just swapping the tags and it swaps them around. And this is a bijection. So next you do the plus is unital. So let alpha be a cardinal, be a cardinal. Then we want alpha plus 0 to be equal to alpha. So I define a bijection between the two things, the thing on the left. So define phi from alpha plus 0 to alpha by, well, what is this? It's a disjoint union of things. So you've got an alpha tagged with a thing. So phi, if it takes an A tagged with a 0, I just map it to A. And there's actually nothing else because you have the other things would be elements of the empty set tagged with a 1, but there aren't any of those. This is clearly a bijection. So we have a unit. Now we want to do multiplication, and the process is basically the same. So next I do times is associative. So let alpha, beta, gamma be cardinals. We want that alpha, beta, gamma is equal to alpha, beta, gamma. Once we've got all this, we can start writing things without the brackets. So it'll be much easier to read. So how do I do this? We'll define a bijection. Define phi from alpha times beta times gamma to alpha times beta times gamma by phi of A, B, C. So here I've tagged the thing in the product with the thing in the gamma. And I just map this to the same thing with the bracket in a different place. This is A, B, C, which is what an arbitrary element of the right thing looks like. And this is clearly a bijection. Yeah, so this phi is a bijection. So they have the same size. Next to do plus is commutative. So times is commutative. And we do the same thing. So let alpha and beta be cardinals. But now I want alpha beta equals beta alpha. So define a bijection phi from alpha times beta to beta times alpha by phi of AB is just BA. And this is a bijection, so these are the same thing. And what else do I want? I want a unit part. I want to define, I want to show that times is unital and that times has a 0. Times is unital. So let alpha be a cardinal. We want that 1 alpha equals alpha. So I define a bijection, define phi from 1 times alpha to alpha by phi. What does an element of 1 times alpha look like? It's a pair where the first thing is from 1, so it's 0, and the second thing is from alpha. Let's call it A. And I'm just going to map this to A, and this is clearly a bijection. So next I do times has 0. So like 0 is sort of an absorber. It absorbs things. 0 times anything is 0, as we're familiar with. So let alpha be a cardinal. Want 0 times alpha to be equal to 0. So define a bijection from 0 times alpha to 0. Well, 0 times alpha are the pairs where the first entry is in the empty set and the second thing is in alpha. So the domain of this is just actually equal to the empty set. Not to be confused with my phi. 0 is also equal to the empty set, so I can just use the empty function. So phi is the empty function, which fits because my phi's look like empty set symbols. So not only are these sets and bijective correspondent, they're just like equal because they're both empty. Okay, and then it's just distributive property. Yep. And note that we only have to do one of these because the other one follows from the commutativity rule when applied to the first one. So I can do distributivity in one go. So distributive. So let alpha, beta, gamma be cardinals. And now I want alpha times beta plus gamma is equal to alpha beta plus alpha gamma. And why does this work? Well, we define a bijection, so define phi from alpha times the disjoint union of beta with gamma to alpha times beta disjoint union alpha times gamma by, and then there's two cases. So what does a thing in alpha times beta disjoint union gamma look like? Let's make this more clear. This is a disjoint union gamma. Well, it's either paired with a beta thing or it's paired with a gamma thing. So phi applied to A paired with B0. I'm going to map it to the thing in the corresponding copy. So it's a B with a 0 tag, and then phi with a, and then now it's got a thing with from gamma, which has a 1 tag on it. This is equal to AC with a 1 tag. And as usual, this is clearly a bijection. It just describes everything on both sides. So now we have all our basic properties of arithmetic, which is pretty cool. Okay, the next bit I want to talk about, I've established all the rules at the front, so we're getting close to being able to deal with, basic elementary school like algebra. I want to do some stuff with exponents as well. And the main thing I want to do is like the carry sort of idea. So exponents. So exponents are nice in terms of how you multiply them and how you multiply the powers. So we also want the following two rules. So for all alpha, beta, gamma cardinals, that alpha to the beta times alpha to the gamma is equal to alpha to the beta plus gamma, and alpha to the beta to the gamma is equal to alpha to the beta times gamma. And we can prove this using the same strats as before, remembering that this is the set of functions from the superscripts to the base. Okay, so let's do this as well. So proof, so let alpha, beta, and gamma be cardinals. And I want alpha to the beta, alpha to the gamma to be alpha to the beta plus gamma. So let's phi from alpha to the beta. Here, this is the set of functions from beta to alpha times alpha to the gamma. So this is like Cartesian product to alpha to the power of beta disjoint union gamma be defined by, okay, I have to take a thing which takes a pair of functions and it assigns it to a single function by phi of, let's say, f and g. And this is a function. So this is a function. So I have to tell you what to do to an element of beta disjoint union gamma. So I take phi to this of this pair and I define it to be a new function. So I define this function by, I take a thing, f, g, phi, and I give it an input in beta disjoint union gamma. So say b0. And what does this do? Well, b comes from the beta part, so I'm just going to apply f to it. And then similarly, if I take a thing in the gamma part, I'm just going to apply g to it. And it's, as you can see before, this is a bijection. I've defined everything you can get from the disjoint union to alpha, because it has to decompose into doing something with the beta bit and doing something with the gamma bit. And I've told you what to do in both situations. If it's in the beta bit, you just do what f does. And if it's in the gamma bit, you just do what g does. And this is a bijection. Okay, and then next, for the last bit, let alpha, beta, gamma be cardinals. And I want alpha to the beta to the gamma to be equal to alpha to the beta times gamma. And again, I'm going to define phi, and here there's not much better notation than this. In fact, it would have been clearer here if I'd written this without the times. So now phi takes a function from gamma to the functions from beta to alpha, and it assigns it a function from the Cartesian product of beta and gamma to alpha. And I do this by phi of f. It takes a function, and I see what it does. This is an element of alpha to the beta times gamma. So I define this function by phi f of beta gamma, sorry, BC, because that's a thing, beta times gamma. And what does it do? Well, it applies f to c, because f takes a thing in gamma, and it gives me a function. This is a new function, which maps from beta to alpha, and I put b into this function, and this gives me an element of alpha. And using the same thing as before, you can check everything is defined in both ways. If I have any function from beta times gamma to alpha, it has to take a b and a c, and so I can assign it backwards a function from c to beta to the, from gamma to beta to the alpha, which takes c and then maps it to the function which maps b to the same thing that f maps bc to. So then, as usual, this is a bijection. So this is a bijection. So we also have our power rule as well. Okay. I think I'm going to continue this in the next video. In the next video, we'll establish properties of finite cardinals and then of infinite cardinals when we actually start doing these arithmetic products properties to them together. So the finite ones, they'll work exactly how we expect, and the infinite ones will be actually quite nice as well. And we'll see that in the next one. Thank you.